Hello students, in this tutorial class I will discuss 6 or 7 problems. So first problem is plane polarized light of wavelength 6000 angstrom is incident on a thin quartz plate cut with faces parallel to the optic axis. So here thin quartz plate is cut in such a way that its face and optic axis they are parallel to each other. Then calculate the ratio of intensities of the O ray and E ray if plane of vibration of incident light make an angle of 30 degree with the optic axis. So if this is the face, here I am drawing the face of doubly refracting crystal or quartz crystal. Here this is the face of the crystal, and suppose this is the optic axis. Here this is the optic axis in x direction, and perpendicular to this perpendicular axis is this one in the y direction. Now a light that is propagating inward the board is incident on this, and its electric vector is suppose this one. The amplitude of this electric vector is suppose A. So a plane polarized light is incident on this calcite plate whose face is parallel to the optic axis, and this electric vector is making an angle 30 degree with the optic axis. Now this electric vector will resolve into two components. One component will be parallel to optic axis, another component will be perpendicular to optic axis. Parallel component, its amplitude will be A cos theta. This will be A cos 30 degree, and perpendicular component will be A sin 30 degree. So this electric vector or electric vibration is resolved into two parts, one parallel to the optic axis, another perpendicular to the optic axis. You are aware that this parallel component, electric component that is parallel to optic axis, this will behave as E ray, and perpendicular component this will behave as O ray. So this A cos 30 degree is the amplitude of E ray. So I can write amplitude of E ray is equal to A cos 30 degree, and amplitude of O ray this will be equal to A sin 30 degree. A sin 30 degree. So now we have to calculate the ratio of intensities of O ray and E ray. So intensity of O ray will be equal to A naught square, and intensity of E ray will be AE square. So we will write this as AO square upon AE square. Now substitute the value of OA and AO and AE here. So this will be A square sin square 30 degree divided by A square cos square 30 degree. This will be tan square 30 degree, and this will be equal to 1 by 3. So ratio of intensities of ordinary light to the extraordinary light will be equal to 1 by 3 here. This is the second question. This is a multiple choice question in which more than one options can be correct. Here question is when an unpolarized light, UPL means unpolarized light or beam, passes through a doubly refracting medium, it splits up into two beams called O ray and E ray. This is known as double refraction. You are well aware of it. We have discussed this in detail in last classes. Consider these statements. We have to find out which one is correct. A part is intensities of both rays are equal. Second is B option is refractive index of O ray remains constant. C option is refractive index of E ray doesn't remain constant, and D option both the rays are polarized. So out of these 4 options, option B, C and D, they are correct. Option B, C and D, they are the correct option. But why they are correct? So one by one I will take these options. So in first option he is saying that intensity of both rays are correct. Intensities of both rays, it means intensity of O ray and E ray, that is equal. Both rays are equal. So what is the meaning of this? Meaning of this is IO, intensity of ordinary light divided by intensity of E, in extraordinary light, is 1. He is saying like this. But in the earlier question, in question number 1, we have already seen that I naught upon IE is equal to tan square theta. And this theta can be 30 degree, it can be 40 degree, it can be 45 degree, it can be 60 degree. See, only if this theta is equal to 45, then IO and IE will be equal. In another cases, this IO will not be equal to, so IO in general it will not be equal to IE, except the case when theta is equal to 45 degree. So intensities of both rays are not equal. So this statement is wrong. So first statement is wrong. Intensities of ordinary light and extraordinary light will be different. Second option is refractive index of O ray remains constant. Refractive index of O ray remains constant. We are aware that ordinary light, it travels with the same speed in all possible directions in a doubly refracting crystal. So refractive index mu, this will be C upon VO. This is the velocity of ordinary light. So this will be the refractive index of the medium corresponding to ordinary light, C upon V naught. When VO is constant in any direction, in all possible directions, so automatically this mu O will remain constant in double refraction. So this option, this B option is correct. In third option, they are saying that refractive index of E ray doesn't remain constant. For E ray, we are aware that this E ray or E wave, it travels with different speeds in different directions. When its speed is different in different directions, so automatically refractive index, which is inversely proportional to 1 upon V, mu is proportional to 1 upon V, so automatically when V is different in different directions, so mu will also be different in different directions. So for this mu O will have different values in different directions. So refractive index of E ray doesn't remain constant, rather it depends on the direction in which the wave is propagating. D option is both the rays are polarized. Here we have two type of rays. One is O ray, another is E ray, and both O ray as well as E ray, they are plane polarized. For E ray electric vibration, they are parallel to the principal section, and for O ray, these electric vibrations are always perpendicular to the principal section. So both O ray as well as E ray, both are plane polarized light. So this option D is also correct. So B, C and D, these three options are correct. First option is wrong. This is question number 3. In question number 3, an unpolarized light is incident on a crystal plate at an angle of incidence 50 degree as shown in the figure. Take N naught equal to 1.6584 and Ne equal to 1.4864. For calcite, the angular separation in degrees between the two emerging rays within the plate is here. This is the incident light, this is unpolarized light. When this unpolarized light is incident on this doubly refracting crystal, it will split or it will give rise to two refracted rays. One is known as O ray, another is known as E ray. So both O ray and E ray, they will travel in different directions. So we have to find out the angular separation between O ray and E ray. First I am considering O ray. So for O ray, apply Snell's law. So first medium is air medium. From air medium, UPL is incident. So NA, refractive index of air, into sine, angle of incidence. Angle of incidence is here 50 degree. This 50 degree. This will be equal to refractive index of the medium for ordinary light into sine RO. Suppose RO is the angle of refraction for ordinary light. So for NA, refractive index of air is 1. This is sine 50 degree equal to, for ordinary light, this is given that NO is equal to 1.6584 into sine RO. This is sine RO. Now by solving this equation, by using the calculator, we can find out that with the help of calculator, we can solve this and we can find out that RO comes out to be 27.51 degree. This is the value of RO. Now apply the Snell's law for the extraordinary light. Here this extraordinary light, for extraordinary light, Snell's law is first medium is NA, air is the first medium, refractive index of air, into angle of incidence will be same for both ordinary and extraordinary. So this will be sine 50 equal to refractive index of the medium for E ray, NE into sine RE. This is angle of refraction for the extraordinary light. Now substitute these values. NA is 1 into sine 50 degree equal to NE. NE is given equal to 1.4864 into sine RE. So here RE can be calculated by substituting the values of sine 50 here, and it comes out to be 31.02 degree, 31.02 degree. So now the angular separation between both emerging rays, delta theta will be equal to RE minus RO. So substitute the value of RE 31.02 here and 27.51 here. So 31.02 degree minus 27.51 degree. Subtract both these quantities and it comes out to be 3.51 degree. 3.51 degree. So this is the angular separation between ordinary light and extraordinary light when an unpolarized light is incident on this doubly refracting crystal at angle of incidence 50 degree. So this is question number 4. In question number 4, E is equal to, this expression represents an EM wave, possible directions of the fast axis of a quarter wave plate which converts this wave into a CPLR. So the 4 options are given here. So they have provided us an expression of an EM wave. Here this is an EM wave, E vector, and direction of E vector is in the direction of 3i plus 4j, and it is propagating in that direction. So first, when I am trying to find out the correct option, I am writing this. Suppose this direction is E0. Suppose this is the E0. Suppose this is the E0 direction. So I am writing E0 equal to 3i plus 4j, and mode of E0 will be equal to under root 3 square plus 4 square. 3 square is 9 plus 4 square is 16. So this is 3 square plus 4 square, and this is equal to 5. Or you can say, so no, not this is this is 5, or you can write it as under root 25, whatever it is. So this is the value of the mode of E naught. So the direction of this E vector is in the E naught direction. Now we have to find out the direction of the optic axis. This fast axis is also known as optic axis. Yeah, you can say optic axis is also known as fast axis. So we have to find out the direction of the optic axis of a quarter wave plate which converts this wave into a circularly polarized light. So a quarter wave plate converts the EM wave, plane polarized EM wave, into a circularly polarized wave when the angle between the incident electric vector is making an angle 45 degree with the optic axis. So the direction between the optic axis and the electric vector of the incident light, plane polarized light, is 45 degree. So what I want to say that we have here 4 options, and the easiest trick is we can find out the angle between E naught and these vectors, and that angle should be 45 degree. How we will do this? So I will choose this first. So first is, suppose I am choosing this option, first option A. So this is A vector. A vector is equal to 1 upon root 2. This is 7I plus j, and A vector and its mode will be equal to 1 by root 2 square root of, this will be 7 7 ja 49 plus 1, this will be 50. Similarly, the second direction is, suppose B. I am representing this by B. So this is 1 by root 2, and this will be equal to minus I cap plus 7j cap. So mode of this will be this one, and this will be equal to 1 upon root 2 under root 1 square minus 1 square 1, and 7 7 ja 49. So this will be again 50. These are the modes, and these are the, now I have to find out the angle in between these two vectors. So what angle these two vectors are making with respect to each other. For this we can use the property of scalar product. So cos theta, I can write cos theta, this will be equal to E naught vector dot A vector divided by mode of E naught and mode of A. So here this is E naught, I have to take this E naught dot A. So 1 by root 2 will be in the numerator, this will be 1 by root 2 here, E naught. So I cap dot I cap, this will be 21. So this will be 21, and 4 into 1, this will be 1. So this will be 25 divided by mode of E naught. Mode of E naught is under root 25, and here this is equal to this mode of A vector is 1 by root 2 under root 50. So what will be here? This is 25, 21. Here this will be 4. This will be 4 into 1. This will be 4. So this will be 25. So this is 25, 25. Under root 25 is here. Under root 25 is here. So this root 2 will convert this root 15 to 25 square root of 25. This 25 root 25, this root 25 will be cancelled out by this. So this cos theta, it comes out to be 1 by root 2, and 1 by root 2 is equal to cos 45. So here theta is equal to 45 degrees. So the angle between E naught and A vector, is 45 degree. Now similarly we can find out the angle between B and E naught. B and E naught. So here if I substitute B in place of A, so here it will be B. So E naught is here. E naught dot B, this will be 1 by root 2 here. This 1 by root 2 will be here. This 1 by root 2 will be here. 7 3 is 21. 21 will be here. This will be 21. 4 1 this is B. Sorry. So this is 1 upon root 2 is here. 3 into minus 1. This will be minus 3 for B. 3 into minus 1 of this B vector. And here this will be 4 into 7. So this will be 28. So minus 3 plus 28, this will be 25. And mod of E naught, this will be square root of 25. And here mod of B, this is again 1 upon root 2 and under root 50. If we solve this, then we will find out this will give us 1 upon root 2. So cos theta is 1 upon root 2 and 1 upon root 2 is the value of cos 45. So theta is 45 degree. So here both these vectors, this vector and this vector, they are making an angle 45 degree with the given EM field. When you will, so this is a correct option, A option is correct here. When you will apply the same method, you can use same method to find out the angle between these directions and the direction of E vector of the given EM wave, then you will find out that this angle is not 45 degree. I am not going to repeat this. This is a homework for you. You have to find out the angle between this E naught vector and all these 6 other vectors. You will find out that these values are different from 45 degree. So in this way, you can find out the correct option. And here we have used the concept that optic axis makes an angle 45 degree with the electric field of incident plane polarized light if on the emergent side we are getting circularly polarized light. So option A is correct here. So this is question number 5. In question number 5, a quarter wave plate is placed in between a polarizer and a photodetector. Here, this is a polarizer, this is a detector, and between them a quarter wave plate is placed. When the optic axis of the quarter wave plate, so this is the optic axis, so this is the optic axis, this is the optic axis of this quarter wave plate, is kept initially parallel to the path axis of the polarizer. So here, this is the path axis of the polarizer and this is the optic axis of the quarter wave plate. Initially they are parallel to each other. The intensity of light passing through quarter wave plate is I naught. So when both this path axis and this optic axis of quarter wave plate, when they are parallel here on this side, I have intensity I naught. If the quarter wave plate is rotated by 45 degree about an axis parallel to the light propagation, what would be the intensity of the emergent light? So now after this initial intensity is I naught, now suppose this is the axis, then this quarter wave plate is rotated around this optic axis, about this optic axis, and by an angle of 45 degrees. So here quarter wave plate is rotated by a 45 degrees. So the angle between the path axis of this polarizer and the optic axis of this quarter wave plate will now be equal to 45 degree. Now you have to find out the intensity here. So I can directly answer this question. Answer of this question is D, because when a plane polarized light passes through quarter wave plate, on the other side we are getting some intensity. So whatever is the orientation of quarter wave plate, that quarter wave plate doesn't change the intensity of the incident light. So whatever intensity is here, the same intensity will be here. But how can we consider this? How can we understand this? Suppose here, I will try to explain you. Here I have an unpolarized light that is incident. So this is unpolarized light that is incident. So this unpolarized light, when incident on this polarizer, then this polarizer will pass the electric components which are parallel to this path axis. So here I will have electric components which are parallel to the path axis. Now these electric components are incident on quarter wave plate. So this is the face, suppose this is the face of the quarter wave plate, and suppose this is the optic axis. This is the optic axis of the quarter wave plate. This is quarter wave plate. So these electric vectors which are emerging from this path axis, they are parallel to this path axis, and initially this path axis and this optic axis, they are parallel. So these electric vectors will incident on this parallel to the optic axis. These electric vector will incident on this parallel to this optic axis, and they will propagate through this quarter wave plate as E ray only, and this will remain plane polarized light on the emergent side. So on this side we will find out, initially we will find out plane polarized light, and its amplitude will be the same. Whatever is the amplitude here, we will have same amplitude here, and intensity will be same. If here intensity is I0, here we will have same intensity, because here there is no O ray, so there is no question of phase difference or path difference that is introduced by this quarter wave plate. So whatever intensity is here, we will have same intensity we will get here. Now what is happening in the second case? Now what they are doing, so this is the optic axis. In second case, when you have rotated this optic axis by a 45 degree, then these electric vectors are incident on this quarter wave plate at an angle, and they are making an angle 45 degree. Here this angle is 45 degree. So now these electric vectors, after rotation of the quarter wave plate, these electric vectors, they are making an angle of 45 degree with the quarter wave plate optic axis. Now what will happen, suppose this was the initial amplitude A. So here in perpendicular direction it will be A sine 45 degree, and here parallel to the optic axis it will be A cos theta, A cos 45 degree. So what we have? We have amplitude E naught x equal to A E naught. If suppose this is suppose x axis and this is suppose y axis, then Ex is equal to A sine 45 degree, and this will be A upon root 2. And E naught y will be A cos 45 degree, and this will again be A upon root 2. So what will be the resultant amplitude on the emergent side? On the emergent side, resultant amplitude will be under root E naught x square plus E naught y square. So here it will be A square by 2 plus A square by 2. So here on this side, on the emergent side, again we will have an amplitude A. Rather in second case, because incident electric vector is making an angle 45 degree with respect to this quarter wave plate, so on the emergent side we will have CPL, circularly polarized light, but its resultant amplitude will be A. Resultant amplitude will be A here. So automatically intensity. So intensity on this side will be, suppose I1 here. So this will be A square and it will remain same I naught. So basically on the emergent side we are getting the same intensity. So the role of quarter wave plate here is to change the polarization of the incident plane polarized light. In the first case, when pass axis of the polarizer, and the optic axis of the quarter wave plate, they are parallel to each other, then on the emergent side we will get plane polarized light. But when this quarter wave plate is rotated by 45 degrees, then this electric vector is striking this quarter wave plate at an angle 45 degree with respect to this optic axis. So now on the emergent side we will have circularly polarized light, but its component, we will have two components, Ex and Ey, and amplitude of these two components will be E naught x, E naught y, and they comes out to be A upon root 2 and A upon root 2. So resultant amplitude will be square root of E naught x square plus E naught y square, and this will be equal to A again. So now intensity will be square of this A, so again its intensity will be I naught. Here I am assuming, here at this point I am assuming that amplitude is equal to A, and this is the resultant amplitude. You can say this is resultant, this is resultant. So resultant amplitude is A here. So on the emergent side intensity will remain same, however polarization will be changed. Now in first case you have CPL here, but now this time we have circularly polarized light. So initially here we have PPL, plane polarized light, and now in second case after rotation you will have circularly polarized light, but intensity in both cases will remain same. So option D is correct here. So come to question number 6. Question number 6 is also based on retarding plate. Here the values of refractive indices for O ray and E ray, N naught and Ne for calcite are 1.642 and 1.478. So basically they have provided us the value of NO. NO is equal to 1.642 and Ne is equal to 1.478 respectively. Calculate the phase retardation for lambda equal to 6000 angstrom with the plate thickness 0.04 millimeter. So for this plate, part difference will be equal to N naught minus Ne into T. If T is the thickness of the plate, then part difference between O ray and E ray, optical part difference traveled by O ray and E ray will be N naught T and NET, and their difference will be N naught minus Ne into T. And we can convert this part difference into phase difference by multiplying this by 2 pi by lambda. So this is the phase retardation that will be introduced by this retarding plate. So phase introduced by this plate will be delta, and this delta will be equal to 2 into 3.14 upon lambda. NO is 1.642 minus Ne, this is 1.478. Here this lambda is given equal to 6000 angstrom. So this is 6000 into 10 to the power minus 10 meter. So convert this lambda into meter and multiply this T. T here is 0.04 millimeter. This is 0.04 millimeter. So I will convert into meter by multiplying this by minus 3. So here from this formula, by solving these values, we get that delta comes out to be 68.66 radian. So much of phase is introduced by this plate. So this is an example of retarding plate. In retarding plate, basically the optic axis is parallel to the phase, and when light when a plane polarized light is suppose incident on this, and this plane polarized light electric vector is making some angle with the optic axis, then it will it will resolve into two components, one parallel to the optic axis, another perpendicular to the optic axis. Parallel component will act as E ray, perpendicular component will act as O ray, as a result of which both O ray and E ray, they are traveling through a distance t. So in this duration they will travel optical path NOT and NET respectively, and difference will be NO minus NE into t. So this is the path difference. If I multiply this by 2 pi by lambda, this will provide me the phase difference that will be introduced by this plate in between O ray and E ray. By substituting these values, we find out delta, and this delta comes out to be 68.66 radians. This is question number 7. This is based on quarter wave plate. So question number 7 is, what is the minimum thickness of a quarter wave plate if the material has mu O is equal to 1.553 and mu E, refractive index of E ray, is 1.544 at a wavelength of 6000 angstrom. So we have to find out the minimum thickness of quarter wave plate. For quarter wave plate, this mu O minus mu E into T, this is the optical path difference covered by O ray and E ray in the quarter wave plate. This should be equal to lambda by 4. So this is the formula for quarter wave plate for minimum thickness. So mu O minus mu E into T, this is the path difference that is traveled by O ray and E ray respectively, and this should be equal to lambda by 4. Then this plate of thickness T will start acting as a quarter wave plate. So substitute the value of mu O and mu E. Mu O is here 1.553 minus mu E is 1.544, and T we have to calculate, and here lambda is equal to 6000. So this is 6000 into 10 to the power minus 10 meter divided by 4. If we solve this, then we can find out that T comes out to be 1.67 into 10 to the power minus 5 meter. On solving this with the help of calculator, you can find out that thickness of quarter wave plate comes out to be 1.67 into 10 to the power minus 5 meters. So here for quarter wave plate, the formula is the optical path difference between the O ray and E ray, it should be equal to lambda by 4.